So today we are going to derive a microscopic picture of Ohm's law, the law that relates the electric field in a conductor to the current flowing in the conductor. Now, last time we've seen Ohm's law in the following form, relating the current density in the conductor to the electric field with a proportionality constant sigma, which is called the conductivity. This conductivity sigma is a property of the conductor itself. Sigma is going to be different for copper or for aluminum or for gold or for platinum. And what we want to do today is to understand how to relate the value of this conductivity sigma to some microscopic features of the conductor, whether it's copper or gold or aluminum. There should be differences between copper and gold and aluminum in a microscopic sense. And we want to understand how the microscopic differences between one material and the next translate into differences in the value of this conductivity sigma. So let's remind ourselves what the picture that we have is, going back to last time. So what's actually happening in a conductor is there are electrons whizzing around, and those electrons are what are carrying a current. And the picture that we have in our heads from last time is of electrons whizzing around at some very, very, very high speed, bouncing around, scattering, changing directions, and moving very, very fast. And I was trying to show you in that cartoon, or maybe better, caricature, give you a sense of a picture in which the electrons are whizzing around very, very fast and at the same time are slowly drifting this way with some drift velocity. And when I say they're whizzing around really fast, I really mean fast, because in copper, for example, it turns out that the speed of the electrons as they're whizzing around is actually about 100,000 meters per second. And when I say that the drift velocity is slow, I really do mean that it's slow, because it turns out that for a reasonable electric field, like you might have in a wire in some electric circuit, copper wire in an electric circuit, driving a current through it, doing something in your phone, for example, for a reasonable electric field in a copper wire, the drift velocities are less than a millimeter per second. In fact, less than 1/10 of a millimeter per second, typically. So this is our basic picture. We had this last time. Electrons whizzing around, whizzing around, whizzing around. But because of the presence of an electric field, which if the drift velocity is going that direction, then the electric field must be pointing this way, because remember that electrons are negatively charged. So because of the electric field, which is pointing this way, these electrons, which are rattling around in here very, very, very fast, are very slowly drifting this way. And we now need to understand how to relate this picture, this microscopic picture, to the conductivity. And the person who first did this, the person who first came up with a microscopic model for conductivity, was a physicist named Paul Drude. And so what I'm going to be walking through here is in fact known as the Drude model of conductivity. So I'm going to be walking through a derivation of Paul Drude's model for conductivity. Paul Drude came up with this model back in 1900. So how did he think about this? How did he relate what's happening here in this picture? Electrons rattling around, high speed, slow drift this way because of an electric field pointing that way. How did he relate that to a conductivity? Let's walk through. His thinking. He made a number of key assumptions. The first assumption that he made is that he assumed that electrons scatter on average once per some time tau. So this time tau is a property of the material in question. It's the first of two properties of the material that we're going to introduce. So assumption number one in Paul Druda's model is that these electrons, they're flying around at some very, very high speed, and once, on average, once per time tau, it doesn't mean that every single time they travel tau on that scatter, but on average, once per time tau, they bump into something and scatter. So scatter means change direction. And this quantity tau, this time tau, is a property of the material. It's going to be different for copper than for aluminum, than for gold, than for silver, than for platinum. So this is our first material property. Second assumption he made is, and introduces the second material property, he assumed that there are n electrons per cubic meter. And in fact, in copper, this n is well known, and I'm not going to give you numbers with a lot of precision today, but n turns out to be roughly 10 to the 29 per cubic meter. And this is the second material property that's going to come into the derivation. So again, n will be different for copper, for aluminum, for silver, for gold, for platinum, for tungsten. Actually not that different, but it will be different. Tau varies quite a lot, in fact, from one metal to another. N does vary, but not by enormous amounts. So I have a material, let's say copper is my example, which I characterize microscopically by how many electrons it has per cubic volume, n, and by, on average, how long does it take between one scattering and the next. Those electrons are whizzing around. How long in time do they whiz between one scattering and the next on average, and that's tau. And so now we want to relate n and tau somehow to this conductivity sigma. So before we go through the derivation, let's try and guess the answer. This is often an incredibly valuable thing to do. Let me just think about this for a minute. So from my intuition as to what conductivity means, conductivity is about the current being carried through the wire in the presence of a given electric field. It certainly feels reasonable to me that this conductivity should be proportional to the number of electrons per cubic volume. If there's more electrons present, then with a given electric field, I'm going to get more current flowing. So I feel like sigma should be proportional to n. Also, although I'm less sure of this intuition, it seems to me that if the electrons fly a long, long way and fly for a long, long time before they get deflected, that's probably going to translate into a large conductivity also. That's just sort of my intuition anyway. You can have different intuition at this point. We'll see whether mine is correct. So my intuition is that sigma should end up being proportional to n times tau. Now you can go and do dimensional analysis and you can check the units of sigma are not the same as the units of n times tau. So there must be something else here. And at this moment, I'm not quite sure what to put here. So this is incomplete, I know. But I have this intuition that sigma should be proportional to n times tau. Now, why did I walk you through my intuition instead of just launching into the derivation? It's because I want you to do this anytime you think about a derivation for the first time. Before you go into the derivation, try and guess the answer. Before you go into the derivation, try and guess the answer. Now, what could happen, we could go through the derivation and we could find an answer that agrees with this. That's incredibly important. That tells you that your thinking was correct. Your intuition was good. Now, it could also happen that we go through the derivation, we get something that does not agree with us, and that is even more important. That's even better. Because if you make a guess at the beginning before you do the derivation, or you go through the derivation, you get something different, then you actually learn that your intuition was not correct, and you have to go and rethink through your intuition and figure out what the right intuition is behind the result in the derivation. So either way, guessing the answer first, always a good strategy. Okay, so there's our guess, incomplete because there's a dot, dot, dot. But actually, if you tried to do a derivation based on what we've assumed so far, you actually can't get any answer. You need one more assumption, and this was in fact Druda's most important assumption. So Druda's third assumption, which turns out to be critical, is that he assumed that after each scattering, the direction of the electron is random. So this doesn't have to be. After all, if you have an electron coming along like this, and now it bounces off of something, maybe the direction it bounces will depend on the initial direction. You know, maybe it's more likely to scatter by small angles than big angles. This assumption says nope, nope, nope. This assumption is this electron's coming along, it scatters, and now it's completely random what direction it's going next. It could just as likely be going this way as going that way. So it's a very big assumption here. And the other thing, by the way, remember that all this is happening inside copper or silver or gold or aluminum. These are all materials in which the ions, the things that are not the electrons, the ions, have a crystal lattice. They have a crystal structure. So maybe the direction of scattering might somehow depend on the underlying crystal structure. But Drude decided to see where he could get what he would get by assuming that the direction of the electron is random after each scattering. This turns out actually to be a pretty good assumption. It's not precisely accurate. In a later course in physics, you can learn more about this and do somewhat better. But this actually, Drude did very, very well with this simple model. So let's keep going. Now actually we have enough. Everything on the board now, this is all we need. So now let's see where we go. Okay, so I have electrons flying at high speed, whizzing along, then they scatter, they go in a random direction. Well, what happens between scatterings? Between one scattering and the next, the electric field curves the trajectories. So we now have the last piece of the picture. This is where the drift velocity comes from. So I have an electron, it's flying along, and there's an electric field which is pointing that way. That means the electron feels a force in that direction. Remember, electron's charge is negative. So I have an electron which is flying along between one scattering and the next, and it doesn't go straight. It gets curved. Its trajectory gets curved like this. Then it scatters. Now it's going in some new random direction. Let's say now it's going this way. But again, it does not go straight. It's feeling an electric force pointing this way, so its trajectory curves. So the picture in full is I have 10 to the 29 electrons per cubic meter. They are rattling around at an incredibly high speed, in copper about 100,000 meters per second, whizzing around very, very high speed. Once every tau, they scatter. When they scatter, they go in a completely random direction. But between one scattering and the next, as they travel about a time tau, they're not going straight, they're being curved. They're being curved because of the electric force that they feel. Electric field points this way, electric force points back that way. So let's be a little bit more precise about what happens between scatterings. So between the scatterings, what does the electric field do? It curves the trajectories, yes. And the way I'm going to make that quantitative, instead of describing it in terms of a curvature of a trajectory, I'm going to say that the electric field gives each electron a little bit of extra momentum. And that extra momentum is called the drift momentum. It's the extra momentum that comes from the push that the electric field applies, which curves the trajectory. And that extra momentum we're going to call P drift. And how big is that extra momentum? Well, when I have a charged particle flying for some time tau, feeling a force, the momentum that it picks up will be the force times the time over which the force is acting. So what's the force? Well, the force is the charge of the electron Q times the electric field. Remember that Q is negative, so the force points in the opposite direction from the electric field. And the time over which this force acts between one scattering and the next is tau. So between one scattering and the next, the electric field gives each electron a little bit of extra momentum, P drift, which is Q times E times tau, and it's a momentum which points in the opposite direction from the electric field. So the electric field this way, the drift momentum that way. Okay, so we're almost done now, although it may not feel like it. What we're going to do next is we're going to write down J and see what we get. So let's work out what J is. We're going to do so using a result that we derived in the previous video. So in the previous video segment, we saw that J in a conductor was N, the number of charge carriers per unit volume, Q, the charge of each charge carrier, here they are electrons, times the drift velocity. And, well, I can relate the drift velocity to the drift momentum very simply by noting that P drift is M times V drift. So this is NQ divided by the mass of the electron times P drift. And now I take my result for P drift from over here and I substitute it in there, and I get a result for J. Let's see what I get. So J is N. There's N. So J is N, a Q, and another Q from here. So that gives me Q squared. And then I have an electric field, a tau, and a mass of the electron. So I'm going to write the tau there, and the mass of the electron here, and put the electric field last. And now I get to say ta-da, because I have J is equal to a constant, here's my constant, times the electric field. So this constant that I've just circled is the conductivity sigma. So I've just derived the Drude result for conductivity, which is that the conductivity of a metal is given by the number density of charge carriers times the square of the charge of those carriers divided by the mass of the carriers times this characteristic time tau between scatterings. And that is our result. And now let's first of all check signs. Notice that J is in the direction of E. It's a good thing. That was part of Ohm's law originally. And in our picture, there was this drift velocity in this direction, but that was negative electrons going in this direction. That means that the current density, J, was going that way, which was the direction of the electric field. So J is in the opposite direction of the drift velocity because the electrons are negative. And that translates into a conductivity, which is positive because the conductivity goes like Q squared. Because the drift momentum is in the opposite direction of the electric field, and the electric current is in the opposite direction of the drift momentum. Two negatives when you square. When Q is negative but squared, it's positive. J is sigma E, sigma is positive. So the signs all work. Now, what about my intuition that I started with? My intuition was that sigma should be proportional to N times tau. And look at that, my intuition is confirmed. So this was a case where my intuition led me in the right direction, and I don't have to go back and review it, figure out how to change it. The conductivity does indeed turn out to be proportional to N and proportional to tau. And when I was thinking just intuitively, I didn't know what the dot, dot, dot was. Now I do. The dot, dot, dot is Q squared over the mass of the electron. By the way, because I knew the answer, I could have tried to fake it and continue my intuition further. I think actually I could have convinced you that it was intuitive that sigma should be inversely proportional to the mass of the electron. I think I could have waved my hands and said, look, it kind of feels like if electrons were very heavy, they wouldn't move very much, J would be less. I would really have had to work to come up with an intuitive argument for the Q squared. Basically, if I had done that, I would have redone the whole derivation already. And so, in fact, the most important thing that you get from the derivation that you don't get from the intuition is the Q squared here. Okay. So where are we? We have an answer. We have an answer for the conductivity, which is a macroscopic quantity that arises in Ohm's law. So this is the conductivity in Ohm's law. In terms of microscopic physics, the microscopic properties of copper or aluminum or gold, N and tau, and fundamental constants, the charge of the electron and the mass of the electron. So let me end by putting in numbers. So I've already given you some sense of numbers for copper. Let me finish that. So I've already told you that N is around 10 to the 29 per cubic meter. Q and the mass of the electron are fundamental constants of nature. You can look them up. But what about tau? Well, from Druda's result here, you can actually get a sense of tau using the measured value of sigma. So you can go look up the conductivity of copper. And using the conductivity of copper and this expression, you can then reverse engineer it and pull out an estimate for tau. And when you do that, it turns out that tau is about 3 times 10 to the minus 14 seconds. That's the time between scatterings for electrons in copper. So is this reasonable? Let's ask ourselves whether this is reasonable. I mean, if 3 times 10 to the minus 14 seconds, if that's the time it takes an electron to go halfway across a copper atom, I would say this would be a completely unreasonable result, and the whole thing wouldn't make any sense. It also seems unlikely that tau is the time it takes electrons to go a mile. I don't think electrons travel 1 mile through a copper wire between one scattering and the next. That doesn't sound right to me either. So let's see, to see whether this is reasonable, let's turn this into a distance. So the distance between scatterings, well, what is the distance between scatterings? Well, it will be v times this tau, where v is not v drift, but v is the 100,000 meters per second. V is the whizzing around speed. So 100,000 meters per second times 3 times 10 to the minus 4, that gives me about 3 times 10 to the 9 meters. 3 times 10 to the 9 meters is about 3 nanometers, or it's about 30 angstroms. And the size of a copper atom is about 1 angstrom, 1/10 of a nanometer. So what this says is that the average distance between one scattering and the next is about 30 times the size of a copper atom. And that's, in fact, quite reasonable. So what we've learned, our microscopic picture of Ohm's law is now complete. What we've learned is that what's happening in copper, if I have a copper wire, and I've got a battery which is driving a current through it, there's an electric field pointing this way, which is pushing the electrons through the copper wire. And those electrons have an average drift velocity, which is tiny. Where does that drift velocity come from? Well, it comes from these electrons, which are whizzing around very, very, very high speed. About every 30 angstroms, which is 30 times the size of a copper atom, they scatter. And between scatterings, their trajectory is curved very, very, very slightly by the electric field. And it's that force that the electric field applies curving the trajectory which gives you a small drift momentum, a small drift velocity, and which is responsible for the conductivity of copper, which turns out to be given by this expression. And this then is the way we relate the microscopic properties of a material like copper to a macroscopic law like Ohm's law.